Hey everyone, and welcome back to our electronics tutorial series. So today we are going to continue on the topic of op amps. This is our last video on the subject of op amps, and it's a pretty cool one, at least I think so. So today we're going to be talking about how to use op amps as oscillators. Now, oscillators have a really important role in a lot of different designs. They're really important in a lot of applications for electrical engineering, and this is a good way to get a nice simple one going. It's not going to be a very powerful one, especially for places like RF or very high power applications, but it is going to be a good way to get you started and maybe get you familiar with the concept of a very basic oscillator. So let's go ahead and jump right into it. So up at the top, I'd like to start with the definition of these things that we're talking about. An oscillator is a device for generating an oscillating electric current by non-mechanical means. So there are mechanical means of making an oscillation, but this is about electronics. We don't want to learn about mechanics, so we're going to talk about the ways we can do it electrically. So oscillating electric currents, all that means is that they shift directions periodically. Okay, so it's either on or off, or flowing one direction and flowing the other direction. So something like a sinusoid, this is oscillating because it's going back and forth, and it'll continue this pattern forever. So we want to try and make something that can resemble that signal. So we can actually use an op amp in order to do this. Just have an op amp displayed here. So op amps are, not op amps, oscillators are actually going to require positive feedback. So if you remember, for amplifiers, we needed negative feedback, and that kept the output stable, made sure that if there was no input, then there would be no output. So negative feedback makes our designs stable and makes them require input. So that's going to be really good for an amplifier. Oscillators, we don't want them to be stable, or we don't want them to require input. We want them to be able to just run on their own. So we need them to actually be inherently unstable and require no input. So we're going to need positive feedback here. So we're going to use positive feedback. And just a brief way that you can think of maybe this being unstable, if you consider maybe V out being connected directly to Vin plus, then if Vin plus goes high just a little bit, V out is going to go high, it's going to push Vin plus higher, and then we can actually use a little bit of a different way in order to maybe make this oscillate. Okay, so we're going to talk about one design, even though there are a whole lot out there. We're just going to analyze a very basic oscillator. So let's jump right into that. So this is the configuration for our simple oscillator. Now, we're going to have to do a little bit of what I call wonky analysis, but we're going to get through it no problem. So we're going to say that we only have 10 volts and ground because we don't really care about this going to negative, although you can definitely have it go that way if you'd like to. And what we're going to do is that we are going to start off by looking at our voltages here, trying to figure out what voltage we have at the very beginning. Okay, so what we have at the very beginning, well, we have a 10 volt input here. We're going to assume everything starts off at 0, so we have a 10 volt input here. Current is going to flow through this resistor, through this one to ground, and then also through this one to the output. Okay, so we're going to assume that everything starts at 0, so we're going to assume our output starts at 0 volts. Okay, so we have 0 volts here, we have 0 volts here, and the capacitor is not charged at all. Now, once we initially turn this on, what we're going to have is that we are going to have this 10 volts here. It's going to start charging up this input, okay, and pretty much immediately, what's going to happen is that this is going to create a non-zero signal on the input, a positive non-zero signal. That's going to cause it to go high. Okay, so that's going to immediately make our output go high. Now, remember, we started off at 0 volts here, and the only path for this voltage to change is through this capacitor. And capacitors don't like to have their voltage changed immediately, so it's going to take a little bit of time for this capacitor to charge. So this voltage isn't going to change immediately, but we'll get to that here in a second. So we need to first calculate what this value is here. Okay, so we need to calculate what our input value is. Well, we have 10 volts here. That's going to cause current to flow through this 10K resistor. We have 10 volts here. It's causing current to flow here. So all of these voltages actually have to go down through this bottom one. So let's simplify this a little bit over here. So we have 10 volts. Oops, excuse me. So we start off with our 10 volts. We have this 10K resistor here. So this is this 10 volts. Okay, so that's that 10 volts there. And we also have 10 volts from our output. Okay, oops, I forgot my resistor again. 10 volts from our output. Okay, and then those are tied together at this node here. And then there's also another 10K resistor to ground. So these are all 10K, and that'll become important. Now, from our circuit analysis series, you might actually be able to see if these are both at the same potential, which they are, 10 volts, then we can actually approximate these as being in parallel. And two 10K resistors in parallel, it's just the same thing as a single 5K resistor. Okay, and go back and watch that circuit analysis series if you're maybe unsure about this. So we still have our 10 volts at the top, a 5K resistor here. And this, again, this is this node here. This is our Vn plus. So I'll put V plus here. And we can now calculate what V plus is. So this is just a simple voltage divider. And if we calculate V plus, that's going to be about 6.7 volts. Okay, so we have 6.7 volts here. Great. So now we've got our 6.7 volts. I'm going to erase all of this because we're going to need more room later on. So we know what our positive input voltage is. Now, we know that we have 10 volts on the output. Current is going to begin to flow through this resistor, and it's going to start charging up this capacitor. So this capacitor voltage is going to start looking something like this. Okay, so it's going to start growing exponentially like that, except it's going to reach that point where it can't be charged anymore. So it's going to kind of grow like this. So it's going to continue growing. We have 10 volts, and if we just let it go forever, if we maybe didn't have this connected to our negative input, it would grow until it approaches 10 volts after a really long time. But something pretty cool happens. So remember, by the time that this negative input goes above our positive, our output flips. Okay, so what's going to happen is that, let's say this is 6.7 volts here. Whenever this voltage becomes greater, so whenever this becomes greater than 6.7, this output is going to immediately flip from 10 to 0 volts. Okay, so let's analyze whenever this case is 0 volts, okay? So this is no longer 6.7 volts because we relied on this 10 volt output. So now let's try and calculate it again. So we have our 10 volt from our input, resistor, and then now our output is still, through a resistor, except now our output is 0 volts, so it's almost like ground. Okay? And then we have another 10K resistor that is connected to ground, so these are all 10K still. All right, so these two that are both starting from this node and going to ground, these are in parallel again. Okay, so these are in parallel, and we can rewrite this circuit with those two 10Ks in parallel to be 5K, just like before. So we have 5K. And remember, this is our V plus, so this is what we're concerned about. So now, if we have this voltage divider flipped, our V plus is just 3.3 volts. So before, our V plus was 6.7, but once this negative terminal gets greater than that 6.7, our positive terminal flips to 3.3 volts. Okay, so now our positive terminal is 3.3 volts. Our output is 0 volts. And this capacitor, remember, it doesn't like having its voltage changed instantaneously. So this capacitor is still at 6.7 volts. Let's get this initial drawing made. So that capacitor charged up to 6.7 volts. And now it's going to start discharging. See? Because now we have 6.7 volts across our capacitor and 0 volts at our output. So it's going to start discharging through this resistor. Okay? So maybe now this capacitor is going to look something like this. Oops. This is a little bit tricky. So our capacitor is going to start discharging kind of like that. Now, again, once it reaches this 3.3 volts, so this capacitor is going to discharge, and once it gets below that 3.3 volts on our positive terminal, the output's going to flip again. Okay, so the output is going to flip back to 10 volts, and then we're starting at 3.3 here. This immediately changes back to 6.7, and then we're just going to keep on oscillating like this. So our capacitor voltage looks something like that, like a sawtooth waveform. And if we just watch this go out forever, our output waveform, let me make this a little bit longer so we can extend it. Our output waveform, remember it started off high, and then went low, and high, then low. Our output waveform is going to look something like that. Okay, so now we actually do have an oscillation. Now, I haven't gone too far into the math on the capacitor and the resistor, how it charges and discharges, and how long it takes, because then it gets super duper math heavy. Okay, and I don't want this to be too very math heavy. I just want this to be kind of a conceptual understanding. Okay, but if you are interested in the math, this is some of the math behind the charge and discharge time, the period, and the frequency. Okay, so you can see that our charge and discharge time for our capacitor is related to our feedback resistor, RF, and our capacitor. So a bigger capacitor is going to take longer to charge, and a bigger resistor is going to reduce the amount of current that can flow. So it's also going to make it take longer to charge. Oops, excuse me. Now our period is 2 times this charge and discharge time, okay? Because the charge and discharge time is symmetric, because we're using all 10K resistors here. We're using all 10K resistors here. So our charge and discharge time is symmetric. If we weren't using all 10K, then this does become a little bit more complicated, okay? But for us, it's symmetric. So our period is 2 times the charge and discharge, ends up being this value here. Now lastly, our frequency. Our frequency is just 1 over the period, so it's 1 over this value here. So if we want to maybe have a higher frequency, we would need a smaller capacitor or a smaller resistor or smaller feedback resistor, okay? Now I did make a note, these work only for the symmetric case, so using 3 of the same resistor values. They don't necessarily have to be 10K, they could be 1K, 100, doesn't matter. But they just have to be all the same. If you start using different resistor values, then you're going to start changing the charge time or the discharge time, and it's not going to be as symmetric, okay? Now in the very beginning, we did have this initial charge time that we first have to charge that capacitor. It takes a little bit longer time, so maybe our output waveform looks a little bit more like this. So we start off with a little bit longer time. We start off with a little bit longer time to charge, and then we start doing charge and discharge periodically like this. Okay? So this is a really, really simple oscillator that you can make with just an op amp and 5 components. So if you do have the components, I do encourage you to make it, and if you don't, plug this into LT Spice. See if you can get a simulation that shows how this is all working, okay? Because this is actually a pretty important understanding. You can probe all these different points to see maybe how this capacitor voltage looks, and maybe the effect of changing a bunch of these different resistors or changing the feedback resistor, stuff like that, okay? Now, the world of oscillators is very deep, and this is actually all the oscillator discussions that we're going to have for the entire electronics series. You can make oscillators with a whole bunch of different components, but then you do have to definitely get pretty math heavy and have a pretty in-depth understanding of things like the Laplace transform or feedback control theory, which is just really, really math heavy, and no one wants that. But as long as you have that conceptual understanding, you're going to be just fine, okay? So once again, if you do have any questions, please feel free to leave them in the comment section. I'm more than happy to answer it. If you do like this content, please give me a thumbs up and subscribe. It keeps me very, very highly motivated. Other than that, thank you for watching, and I'll see you next time.